Yes. I did not get you. What did you say? Assignment questions? Okay. Well, they should be similar. To be frank, I have no idea about how the question paper is set up for the final exam. Uh, okay. Okay. Actually, I am just a teaching assistant. I don't set up the questions. So, to be frank, I really don't know how the exam question paper is set. I don't think it will be very far away from what you're doing in assignments. Should be at least the concepts will be similar. Yes. Yeah. Yeah, yeah, you can just check it. I confirmed with the NPTEL team there was some technical issue, that's why it was not showing up on the page. Now you can see the problem solving session, I guess. That's what they wrote. That section is there on the left bar where you have other lectures and other things. So maybe just you can just check it. Yeah. So that will contain both the notes that I'm writing during the session as well as the YouTube links, which YouTube links anyways, you people would have got it by directly searching for the course code. But yeah, it's also present there. Okay, so I think we can start our session. Yeah, many people are joining. Okay, let's start. So yeah, today's discussion will be based on week 8 lectures for the course uh, computer vision and image processing. I hope you can see my screen. Yeah, now you should be able to see my screen. Okay. So yes, so I think this week we had two lectures. Both were on object boundary detection. So why do you think is required to detect the object boundary? Any applications that you think of? Anyone? Anything that you can think of? It's not necessarily that it should be from a lecture itself. Why do you need object boundaries at first place? So a simplest example would be the one the yes. So the simplest example would be yes, you want to detect the object and you want to just concentrate on the object and leave everything else apart in the sense that you don't want other things in your image. You just want to process the object as such. So that's why you might want to just keep the object boundary as such. So within the object, so if you get the object boundary, you can see the things which inside the object as being used for your further processing. For instance, these autonomous driving cases, they have to detect the objects so that they are not, so the car is not colliding to that object. So that's one of the recent most examples. Of course, there are very old examples as well, but anyways. So yes, there are. So one of the motivation of why do you need object boundary and shape representations, you want to then recognize which shape object it is so that you might want to match it if you are taking pictures from different angles and from different locations as well. You might want to match it that okay, this belongs to the same thing or the same class of object that it has. Okay, so it started with first, anyways, it was describing what's the objective out there. Uh, so the main objective is you just want to focus on the information that you want, and you can remove other information from the image. That's why you want to detect the object boundary as such, and then you can further use the object boundary by storing it instead of storing the full image, which can help in quicker processing in further steps. So, what kind of information is generally used uh, for image representation? Some of them that we saw in the last few weeks is the edges in an image. So the edges in an image gives us good information about how the structure of the scene might look like. The colors can help us understand what's the properties of the object and even the illumination and texture. You can also retrieve the shape from the texture given under some assumptions that we discussed. For this specific week, we will be focusing only on the object boundary and representation. So that's also a kind of information that we can use to uh, yes for the further applications out there. So the first one is the you want a boundary descriptor out there. Assume that you know that there exists an object and you're able to detect the boundary. So once you detect the boundary out there, how to describe it? As I said, that you might want to describe the boundary because if you take the same image from a different source, or rather a different location and with a different orientation of the camera, you might want to detect it whether it's the same object or a different object. So if you have a different, the object sizes and shapes are different, then probably it's easier to get that. So you have to describe it to the computer. Okay, there is a object out there. For that, you need a boundary descriptor. The first one is the simplest one that one can use is the length of the boundary. Do you think it's a good one? The length of the boundary as boundary descriptor. It's always not uh, useful enough that just getting the length of the boundary is a good descriptor out there. For instance, if I have a thread like this, the thread is of length L, for instance. Now you can also have some other curve out there whose length is also L. So both the lengths are similar. They cannot really be distinguished whether with this specific descriptor of length of the object whether they are different or same. So yeah, length is not really a great descriptor. Then you can also see the size of the smallest circle or box that can totally enclose the object. So for instance, if you have a complicated object like this, you might want to enclose it with a box like this. So it's specifically said the smallest size. Why smallest? Any idea? The object out here, and this is the smallest uh, box, for instance. Well, this is not the smallest one, but this is some box out there. I can draw another really tighter box out there. Why do you think this is a better representation than the black box out there? Any guesses? What could be the reason? So, simplest example would be that if you have an image like this, and if your object is here, you want to get, you want to localize the object only on this specific part. You can also take a box like this big as well, but it doesn't really give much information. But if you have a box which is tightly enclosing the object, then you can think of it as it's more informative because you are now able to define a smaller region where you are certain that the object exists. So you need the smallest, you generally take the smallest box or the smallest circle out there for bounding the object. Okay, and then there were a few other concepts that were discussed, which is the shape number, Fourier shape number is okay. We'll go with the shape number. What is shape number? Anyone? Anyone? What is shape number? If someone remembers. So you are trying to quantify something, quantify a specific shape with a number. So that mapping you can think of it like a shape number. But the properties that you first want is, I mean, you have to encode it to some extent. The for one of the uh, methods that was discussed in the lectures are the chain codes, where you try to track the object. Where, for instance, if you have a given starting point, you just track the directions in which the object moves, and based on that, you get a set of numbers. The point is that set of numbers is called as chain codes. The problem is it's not good enough for us to just get a set of numbers because now if I change the starting point, the set of numbers will change completely. Or yeah, or if you change the object to such an extent that you might have rotated the object in this specific direction, even if you keep the same starting point, you will get a different set of chain codes because this is heavily dependent on the direction that you are measuring. So one of the best ways to use it is instead of directly encoding this, we first get the chain code and then get the difference in direction, which is like we have all four directions out there. Maybe this is direction one, two, three, four. I think in lectures it was from zero to three. Yeah, okay. Just maintain that convention. Zero, one, two, three. Yeah, anti-clockwise. So given this, you will see how many directions have changed for a given set of numbers, and based on that, you will try to encode it, which is called as a shape number. And to make it rotationally invariant, you also check for the last and the first element out here. That's what is done to get the shape number. Anyways, we'll be discussing a problem, I guess, at least one problem on this, so it will be very much clear when we do that. Okay. So given this, once we have this specific uh, code, we generally binarize it and then store it or send it to the receiver if required. So given this, next is something that was discussed is, yeah, shape number was done, and then there's a polygon approximation. So what is polygon approximation? Anyone? So if you have a weird shape, I'll use the same shape which was used in the class, almost the same shape. Then if you have a weird shape like this, then you might want to approximate it something like this, probably, given the way you defined your polygon. Uh, yes, so you want to keep it as close to the original shape as possible. Assume that these lengths are same. They're not same in my current diagram, but the point is this one should closely approximate this one. That's the whole idea. So given that, we are able to get a rough estimate of boundary out there. Okay. And then there was distance versus angle signatures. So if you have an object, distance versus angle signature. So if you have objects with varying shape, it is very useful. Very useful when the object shapes are different. Very useful what? What is it? Descriptor. Shape is different. So if we have an object like this, which is circular, and an object like this, which is a square, if you take the center of it and then measure angle and distance, oh sorry, measure distance along the angle from the center, from the x-axis, then what you get is a graph like this. For this case, if d is the distance, or rather, since I'm using r, I should continue using r. R is the distance. We can see that the distance is constant with respect to the angle, and we generally check it for between 0 to 2 pi radians. But here in this case, if you see the angle, this will be the lowest. For theta is 0, it will be the lowest. Theta being 45, it will be the maximum. Pi by 4, pi by 2, so on. So theta at pi by 4 is maximum, and then again it will come down pi by 2 to the same level. So if this is a square of side A, this will be A by 2. This will be what, 2 times A by 2. So this pattern continues like this. So one of the most important thing that I want to mention here is that for all these descriptors, we are encoding the location information. Rather, yeah, the pixel location information, relative pixel location information. And there is nothing to do with and not the intensity. You might detect boundaries using intensity, but try when you try to describe it, you just describe it based on the size of the object or the curvature of the object. So you don't use any intensity information of that uh, object boundary, but you're just trying to encode the relative pixel information, uh, the location information. Why am I saying relative? Because for different cases it turns out to be pretty different. Here in this case, since there is circular symmetry that we enforce to get a shape number, so it's giving us a relative pixel information and not absolutely where exactly the object is located. It's just that, oh, this object is of this shape. That's all that's saying. And for this specific case, since we have a center here, you can get the good idea of where the object is as well. So that's what we are trying to encode here. Yeah, so once this is done, we can, yeah, there was again, as usual, in the other applications, here also we use the statistical methods where we compute the moments. So this is the nth moment for a random variable r, which is for discrete case turns out to be like this. Ri minus m, where m is the mean, which is the zeroth order moment. You can write it like this: mu zero of r. Yeah, and this is your probability mass function. Okay, so if it's continuous, then you use probability distribute density function. But since we are in discrete domain, we are using mass function here. Okay, so given this, this is one of the interesting topics that was discussed, which is boundary segments. So you have to partition boundary using the vertices of a convex hull. So what is a convex hull? Can anyone tell that? Or even before that, what is a convex set? Because if you know convex set, then you can define convex hull, and once you know convex hull, you can use the boundary segments. You will be needing a convex hull to get the boundary segments out there. So yeah, you can unmute yourself and speak out. Fine. Okay, someone wrote smallest polygon enclosing the object is convex hull. Not really the case. Okay, any other idea? First, I'm asking what is convex set. Let's fix to the convex set, and then maybe we'll go move to the convex hull. Simple definition of convex set. So if I have a set, okay, I will not draw the set as such. So I've given 2 points x and y, so that both of them belongs to some set C. What does convex set means? That the line joining the points x and y, it's a straight line. Although, yeah, it's better. The line joining the point x and y will also lie in C. This should also lie in C. Lie in C if C is a convex set. So this is the geometric interpretation of what convex set means. If we want to define it mathematically, you can just take as alpha x plus 1 minus alpha y should belongs to C. If if x and y belongs to C, then x alpha x plus 1 minus alpha y belongs to C for all values of alpha belonging to 0 to 1. 0 and 1 is anyways included because x and y belongs to the set C. And if you see that you take a weighted combination of these 2 points, and then which makes you stay on this line segment between x and y, even if you'll continue to be in the set while remaining on the line segment, then it means that it's a convex set. I hope the definition is clear. So so this also means that take any x and y, take any x and y in C, and then check for this condition. So for all values of x and y, this condition should satisfy. This is the convexity condition. So, okay, so this is what is meant by convex set. So next we move on to convex hull. So before we move on to convex hull, I should discuss a few examples so that it makes more sense. So this is just a 1D example out there. For 2D example, how does it look? Uh, so I'll ask you questions like this. Okay. So hopefully this is a circle. Is this a convex set? These are 2D examples. Yeah. So is it a convex set? Uh, so my region contains the whole circle, sorry, the my set contains both the boundary and the region inside the circle. So is it a convex set or not? Given this definition, yeah, it's a convex set. What about this? This is something like a diamond shape or rhombus. This is filled. Is it convex? How? So if I take any points here and there, all points, this is convex, right? And take any 2 points, all the points lie within the set, right? This is also convex. So what about this specific? Uh, if you would have seen a CD drive, which I don't think exists these days, so it is like a hollow disk where this part is filled and the inside part is empty. Do you think is it convex? Yeah, it's not convex. Yeah. So we are talking about convex sets, not we are not started with convex hull. Someone confused, I guess. So we'll go on to the convex hull. So one more weird shape, which I think this I can call as diamond fully because it's shining. Is it convex? Yeah, no, it's not convex. Yeah, that's right. Because if you take 2 points, these end of these 2 points, they don't lie within the convex set. I'm talking about this being filled. Okay. So now we'll move on to convex hulls. Yeah. So what do you mean by convex hull then? So I just defined convex set. What do you mean by hull? I'll take this specific example of diamond. So I said that this is filled from inside, but then it is not convex because if you take 2 points outside, you have to join them and then you see that they don't exist inside the set. So what you'll do is take all possible points, join them, or whatever is the remaining part that you think is not within the convex set, just add them. So this the thing I'm drawing with purple, I'm just adding it to the existing black set. So this is now a convex set, but the black one is not convex. So the convex set is the smallest. Oh, I should not write like this. So convex hull is smallest convex set. I'm saying smallest because that's by definition like that. You don't want again to cover more area than. So I can. This is also a convex set if you want to define. The point is it's way too far away from the. I will not say way too far away, but it's way too expanded than the original object size. So yes, convex hull is the smallest convex set covering the given set. So this, I hope this specific example is clear that if we add the specific regions out there to the non-convex set, this becomes a convex set, and we are trying to get the smallest. The smallest will give you the convex hull. So I'll just repeat one example back again to make it clear. So this is a circle out there which is filled. Is it convex? How can you, what is the convex hull of it? Yes, it's the same. Convex hull is the same as the circle itself. Because it is already convex, you don't need to add anything more to it. Convex hull for this example is same as that of the circle itself. Well, if with circle I should, I mean it's filled circle, not just a circle, it's filled. Okay, so enough of convex and convex hull. The idea is that where we are trying to use it is for boundary segmentation out there. So if we have a weird complicated boundary like this, like an amoeba, anyways, it's fine. So if we have something like this, how this is a non-convex set, you can clearly see, or rather non-convex object, I would say, and you want to segment the boundaries to some extent. So what will you do is you pick up points, you try adding the specific regions out there to such an extent that the final one, so the final one, I'll draw it like blue. This is the final covering area. This one is now convex. So the point is it would intersect at some points with the original boundary. So these intersection points uh, gives the segments of the boundary. So that's where it's very useful to get the convex hull of a given object. Okay, so given this, there is one more descriptor as Fourier descriptor, which is which Fourier transform is being used. Uh, there are two, three different types of Fourier transforms that was discussed previously. So here the specific Fourier transform is discrete Fourier transform. So you assume that your image is the XY coordinates of the pixel boundary is what is taken as a complex number, is a complex number. And then, so this is our signal part. Once we have the signal part, now we have a signal, we can take a Fourier transform of it. So we take a discrete Fourier transform based on the number of points that you have, and you can see that you can recover the signal to a really good extent. So if you remember the example that was given in the class, if you take an original square shape object and take a DFT, and if you take a fewer coefficients, so this square shaped object, what does it contain? Does it contain low frequency component and high frequency component both? Or does it contain only one of them? The square shape. Any idea? What frequency content does this shape contain? High frequency, okay. Doesn't it contain low frequency part as well? So the low frequency means there is uh, so here it's not the image out there. Here we are sending what? Pixel coordinates. So you have to consider the pixel coordinates as your input signal and not the image out there. So everything is an edge if you see it on the image. The problem is you're sending image coordinates instead of the intensity values. So when we did Fourier transform initially, what we did is uh, we take what? We take the intensity values and then try to take a Fourier transform. But here we are taking pixel coordinates and taking the Fourier transform. So both of them are completely different. So here uh, it contains both low and high frequency points. High frequency because you can see sharp transitions at these corners. These corners are all high frequency parts, and then if you see this specific part of the signal, it is very flat out there. So in effect, you are moving like this. You are representing signal like this, covering these points. If you just write it as an array, so you think this is 0 comma 0, this is 1 comma 0, this is 1 comma 1, this is 0 comma 1. For instance, of course, there are many other points. You can just fill it out there. So you're moving from 0 comma 0 to 1 comma 0 to 1 comma 1 to 0 comma 1 to 0 comma 0. So this specific signal between these things, there is not really a big change. So here in this specific case, only x coordinate changes. Here in this case, only y coordinate changes. Here in this case, only x changes. Here in this case, only y changes. The point is when you see from here to here, you change the direction here. When you change the direction, that creates a big problem out there. Here the direction is being changed, right? So this is the high frequency part. These parts are the low frequency part. So it contains both of them. So given that you are using this pixel coordinates as the boundary, pixel coordinates of the boundary as the signal, you can take Fourier transform. It contains both low and high frequency components, and that's why if you look into the example given in the lectures, you see that if you have a square out there with low frequencies, it will look like a circle. But as soon as you increase the number of frequencies, it will become like this, and at last take almost all of the frequencies, then it becomes almost same as that of the original size, original shape, that is a square shape. Okay, I hope this part is very clear because there's a major difference is we are not dealing with intensities, we are dealing with pixel coordinates for all the boundary descriptors, not just this one. Okay, so yes, there are some few properties out there for these Fourier transforms. Which are the properties of Fourier the properties of Fourier descriptors just come along from the properties of Fourier transforms. We'll do one of them during our questions and we discuss questions. Uh, then after this, the next thing that was taught is a B-spline representation. What is B-spline representation, or rather, what are B-splines? Anyone out there? That is okay. Someone wrote that using control points, having control over the local curve. Okay. Freehand curve, which is fine uh, if you use your hand actually to trace the boundary. But in computer, you need mathematical descriptions, right? So what are B splines out there? So B splines, B splines. If you remember, there was there were different kinds of B splines out there. So for instance, this is one of those B splines 0, 1, 2, 3. This is the x coordinate, and this is one of the functions which is 0, comma 0. This is 0, comma 1, and it is varying with respect to some variable t. Okay, so these basic functions out there, they are the B splines. Yeah, please, people can unmute and directly speak out. Don't have to be that formal. Someone raised their hand, just unmute and speak out. Okay, I think it was a mistake. Okay, yeah, if you have any doubts, just unmute and speak out because I won't be seeing the meeting screen often. Okay, so what are these? These are just polynomials, which are, of course, they are shifted. These are all shifted polynomials of different degrees. So this is the simplest one, which is a constant polynomial out there, but you can take other things as well, like linear polynomials, where you have the order will increase. You have quadratic as well, and then you have cubic polynomials as well. So all these polynomials were discussed in the class, so I'm just skipping it now so that I can quickly go over to the questions. But the point is, this specific combination of polynomials can help you trace the boundary very easily. So if you have a very complicated boundary as such, so I'll use this example from the class that if you have a complicated boundary like this, so there are two different specific things that you can adjust for. The one is the order of least spline, which is whether they should be constant in a region, they should be linear, they should be quadratic, or they should be cubic. That is meant by the order. And the other one is the control points. So to understand it carefully, what will the order of B spline do? So assume that this is the shape of the object, which is kidney shaped object out here, and I'll just put the object again here for reference. Given that I have some control points, just 5 control points out there. So how will the order of B spline really help you? So if I take order, what do you say? Order 1. That means if I take linear functions out there, how will this look like? So I still have these points out there, specific points out there. How will it look? Anyone? So it will just be like joining these dots. So it's not really a good approximation. This is the case when we fix control points and vary the B-spline order. So it will look something like this. But then if you now try to increase the order, for instance, if you take a quadratic order instead of a linear one, then you will see that your curves will be like this. So this one looks much better than order, right? Yes, someone wrote to account for twists. Yeah, so you call it as curvatures out there. At a given point, the curvature might be high or curvature might be low. But if you want to account it properly, you want higher orders. So if you keep the number of control points low, so here the setting is control points are low, then you will need what higher order for these planes. So we'll just do the reverse thing now. So we'll fix B spline order and vary the number of control points. Vary number of control points. So this is my second setting that I'll use to illustrate it. I'll still have the same bean shaped object, but now I'll increase points out here like this. So what if I have okay, I should use the same thing. So yes, as we see that if you have order one out here, you just get very crude approximation of this bean shaped object. But now if I have this, if there are more control points out there, then you can see that even if you do a linear approximation, you can get the shape of the bean to some extent. This also looks like bean, at least to me it looks like bean. So the point is here, we have just changed the setting that control points are high. Control points are high, then you can choose lower order for these planes to approximate it properly. So there is a big trade-off between how many control points to choose and how many and what should be the order of the B splines to effectively represent this. No one generally uses order one because as you see there are too many discontinuities that you see. In the original one it's not that discontinuous. So we generally tend to use slightly higher order, for instance, maybe order 2, but not these many control points. You can just reduce the number of control points to get approximately the shape that you. So this is design choice based on the application. If you actually try to code it, you will be needing it. You will have to make such choices. And then there were other descriptors like topological descriptors, which I think we have questions for that. Yeah, we have questions for that, so we'll discuss as soon as we do the question there. Then we have other descriptors like run length description, quad tree description, all these things we'll do at the time when we solve the questions now. And there are descriptors based. Yes, yes. Okay, okay. Active contours is something I discussed last week or last week. Okay, maybe you can just check it if you want to see more details, like last week, week 7 or week 6 discussion out there. But but just to give you a small idea, I just gave that rubber band example. Uh, in the sense that you want to detect where the object is. So this is the object, and if you have some rubber band like this, so if you place a rubber band like this and leave it, that rubber band will stick to the object. So this is based on what the energy formulations have been given in the lecture notes. So there will be some energy from the rubber band side, which is the contour side, and some energy from the object side. For instance, if you're covering a jar, the object shape will give some energy. So that's something that you can just relate to it. But of course, you can check the specific week discussion for get a better intuitive idea. So given this, we it was also Hotelling transform was also discussed, which was kind of done as KL transform initially. So the core idea here is that the elements are not correlated. In the sense, if you apply some Hotelling transform like this, then if you see covariance of this variable y, it turns out to be like this. So it's only diagonals of lambda 1 to lambda n. So what it means is other each element is uncorrelated in the sense first element is only related to first element and not the second element or any other element. So this really helps during estimation because if you have uncorrelated elements, you can solve them almost individually, you can say, and you can still get a good approximation of what's happening. And this is the same thing that people use for principal components, and this was given as an example there. And at the last, there was an art descriptor, which is angular radial transformation. Yeah, angular radial transformation, which gives us an idea of what class of shape a particular object belongs to, and then maybe you can just search for the specific shape, whether it exists in your database or not, or maybe you want to detect how close the shapes are out there with the given query shape. Okay, so that's it. We can just start the questions now. We'll do the some of the stuff that we skipped through during the discussion now. Okay, so the first question is so yeah. So so we have a theoretical question out there, but I'll show you why this really works. Suppose that a sample boundary of an object is represented by Sk. So we were discussing about the Fourier descriptors. This is on Fourier description of, of the boundary. Okay, so you are given Sk, which is the boundary, and Au, which is the Fourier transform, DFT of Sk. Okay, so if the boundary is translated by S naught, then its new Fourier descriptor will be what? Anyone? So there are three or four properties that were given in the slides, and it uses one of the properties. So if you just blindly check it, yes, there is some uh, A of u will be, or rather A dash of u will be A of u plus S naught times delta of u, where this delta is Kronecker delta. Kronecker delta means we are doing it in the discrete domain because we are taking DFT. But can anyone prove this to me? So the right answer is this one. It remains same except at u equals to 0 because everything else is same, but at u equals to 0, this S naught term gets added out there. Okay, so given this, can anyone prove this to me? Because it's not really easy to remember all this during exams, and one might want to just derive it there itself. So what is AU? Anyone? DFT of SK? What is the formula for DFT? Anyone? DFT? Discrete Fourier transform. So you're going from a time domain or space domain to the frequency domain. Time domain is k and the frequency domain is u. So you have to sum over k if you want to go from time domain to frequency domain. Since you have capital K samples, for instance, if you have capital K samples, you will do it this way. Sk is your signal, e to power minus j twice pi u small k upon capital K. Okay, so this is the DFT of Sk. What we have now is the boundary is translated by S naught. So I told you these are the pixel coordinates and not the intensity value. So if you translate it by S naught, your new transformation should directly add up to that, in the sense that if you just add Sk plus S naught times e to the power minus j twice pi u k upon capital K. This is your specific transformation. Ah, yeah, transformation after S naught is added. Okay. So given this, how to solve for it? One easy thing that we can see is that it still contains AU, right? Yes or no? It's very clear to see this. So I can just decouple this part as UK, this specific part, plus I'll just take out S naught out of summation and then keep the other things just as it is. Okay. So given this, this is my AU plus this is S naught times K equals to 0 to K minus 1, 8 power minus J twice by UK upon capital K. Hope this part is very clear. I have not done anything. I just did some simple algebra. Okay. So now the point is we have to evaluate this summation term out there at the right. Okay. So let's try it out. So the point is this summation term will give us delta of u. That's how I wrote this specific expression. How does it give delta u? Okay. We'll just try to take some specific examples. So let me take, if k equals to 4, how does it look? The summation. K equals to 0 means the first term is e to the power 0, which is 1. The next term is e to the power minus j twice pi u upon capital K plus, and the next term is e to the power minus j twice pi 2u upon capital K plus e to the power minus j twice pi 3u upon capital K. So these are the four terms of the summation out there. Fine. Everyone agrees? If I just expand it, minus. So this is using the Euler's formula, cos 2 pi u upon k. This is sine 2 pi u upon k. I can just write it for the other terms as well, cos 2 pi 2 u upon k minus k sine 2 pi 2 u upon k pi 3 u upon k think this is very fun, everyone. Just expanding it for each of the terms out there. So now take any specific value of u to understand this. I will take u equals to 1 for it. If you take u equals to 1, what happens? I'll just write it again. Cos, I'll take all the terms, similar terms nearby. This is cos twice pi by k. So I'll replace k equals to 4 as well to get specific value. This is cos 2 pi by 4. This is cos 2 pi into 2 by 4. Cos of 2 pi into 3 by 4. And minus j times sine of 2 pi by 4 sine of 2 pi into 2 by 4 plus sine of 2 pi into 3 by 4. Hope this is very clear. I'm just replacing u and k with the respective values which I chose. So given this is what sine 2 pi by 4 or sine pi by 2, which is 1. This thing is 1. This is sine pi, which is 0. This thing is sine 3 pi by 2, which is minus 1. What about this? This is cos pi by 2, which is 0. Cos pi, which is minus 1. This is cos 3 pi by 2, which is again 0. So given this, what we get? This turns out to be 0. So actually, for all values of u from 1 to any other value, this specific value will be 0. But for u equals to 0, what should be the case? Everything you have to replace zeros with here. So which is 1 plus 1 plus 1 plus 1, which is a constant. At u equals to 0, this value will be 4. That means it only exists at u equals to 0, and at the other points they do not exist. This function does not exist. So to normalize it properly, you can just take 1 by k out there. Once you take 1 by k out there, you can easily see that you get this specific expression. So this whole expression will be now 4 into 1 by 4, which is 1. So this is S naught into delta U. So so ultimately we get this specific expression by replacing this in this summation part. Everyone agrees with the derivation? So ultimately this is what we proved. When you shift the boundary by a small by some amount S naught, it ultimately just changes the value at u equals to 0 by S naught, and other values remains the same. Okay. Any doubts with this question? Move on to the next one. So we have, yeah, we just discussed about the chain code for specific boundary. We would like to interpret it. What's the, we would like to compute the chain code based on these 8 directions. So in the classes we have discussed in the 4 direction case, but here we are taking more directions, so it improves the expressibility of the chain code. So anyone who would like to attempt this? how to get the 8 connectivity chain code for the specific problem. Okay, just yeah. So yeah, I'm just using the same. First is 7. Yeah, this one will be 7. And then from here you have to go like this, which is 0. And then this is again a 0. This is 6. This one, 5. Again a 5. Then next this one, 7. Next, 0. This one, 2. This one, 0. This one. Next, 7, 6, and 6. So everyone got the idea how we trace the path based on the direction. We just checked for 1 pixel change in the neighborhood, in the 8 neighborhood, and then assign the direction in which these directions are labeled. Okay. So what we get is 7006557002076. Hope the answer is right. Okay. So any doubts in the specific part? So it's as easy as you see. There's nothing much to do. Just check the directions and then trace the boundary based on the directions, and just report whatever direction that you see. Yeah, in the sense, 2 pixels adjacent. So in the sense, if you see this one, right? This one you're saying. Yeah. Okay. Okay. Got it. This one you're saying, right? Okay. So you can then. Okay. Okay. See, if you just add this specific pixel out there, what what can you do? Of course, now you can directly go down and then continue like this. But your boundary also contains this, right? And what is this specific thing that we extracted? It is a boundary descriptor. So your boundary descriptor is not describing this other part, which is not good. You have to cover it somehow. So what you have to do is uh, you have to go like this and then come like this if you have multiple options. Okay. So your boundary descriptor should contain all the pixels right here. That's the core idea. Okay. Yeah, even here as we see, we just took a 90-degree turn instead of a 45-degree turn, right? Because we have to cover we cannot leave the specific pixel. So in the same case here. Okay, so we'll just move on to a quick extension to this question, which is since we have got this specific what was this? This is chain code based on the 8 directions. Now we have to get the cyclic shape number of this code chain code. So how do we do it? Yes. Difference of what? Okay. So just for your convenience, I'll drop this here. Okay. And this is and the number that you are given is 70065 So we have to check the difference, but difference in what sense is difference in the number of directions that you cross. Okay. So if you go in what direction? In anti-clockwise direction. So we go in an anti-clockwise direction and check for differences. So going from 0 to 1 is like one difference, going to 0 to 4 is four difference, going from 7 to 0 is one difference, but going from 1 to 0 is also seven difference. I hope that's clear because you'll cross 1, 2, 3, 4, 5, 6, and 7. So going from 1 to 0 is 7 difference of the angles that you go. So what we'll do is we'll check for the pairwise differences as you said. So first of all, we'll yeah. So given this specific diagram that we have, we can quickly sort it out. Yeah. So we have 7, 0 out here, right? So going from 7 to 0 gives us a difference of 1. 0 to 0, the difference is 0. 0 to 6, difference is 6. 1, 2, 3, 4, 5, 6, right? From 6 to 5, 7. 5 to 5, 0. 5 to 7, 7 to 0, again 1. 0 to 0, 0. 0 to 2, 2. 2 to 0, 2 to 0, 6. 1, 2, 3, 4, 5, 6, right? 0 to 7 is 1. 7 to 6 is 7. 6 to 6 is 0. So this is what we get when using the chain code. But you have to do is like take the difference in the chain code. But you have to take the cyclic version of it. For cyclic version, we check for 6 to 7 as well, right? 6 to 7 is what? 1. Yes, everyone agrees with the cyclic chain code. So now what we have to do is the cyclic, this is shape number, sorry, not the chain code. So this is the cyclic shape number. Once we have the cyclic shape number, not really, but this is a model of the cyclic shape number. We have to convert so that convert means I'll specifically write it shift in cyclic manner so that what something happens, right? The magnitude of the integer is minimum. Yes, everyone agrees. This was the condition out there. So why do we do this specific thing? So that it's rotationally invariant now. Doesn't depend upon which specific direction that you choose as a reference point. Even if you rotate the image and get the descriptor out there, the descriptor will give you the same answer. Okay. So given this idea, how do we proceed? So we have I see some zeros out here, right? So if the first position will contain zero, of course, our magnitude of the integer, or rather the final number is less. So try to make first position zero. So given the first position, what is the next position that you can take towards the right? It can be 6, which is okay. It can be 2, okay. 0 and 2 is much better in the first two places than 0 and 6. 0 and 2 again, it's the same thing. Okay, now we have to choose the third digit if we don't find a better one. But 0 and 1 is also there. This 0 and this one. So what your cyclic shift to do should do is take this specific thing out there and rewrite it like this. So I'll just shift 0 at the front. So your minimal number will be this. So this is the cyclic shape number because this has the minimum magnitude out there. Is everyone fine with that? Okay. So the whole idea here is that we'll just keep 0 at first place because we want to keep the magnitude low, and then after 0 you can check for the immediate right digit out there, and you want to keep the lowest one. If there is no competing lowest one, just place it like this. If you have competing lowest one, then check for more digits out there. So this is the answer to this question. Any doubts? I guess there are no doubts. We can move to the next question. Yeah. So now you can. So I skipped this part during the initial discussion, but we can go to the details now. So you have to find the Euler number of the following shape. What is Euler number? Okay. E is some C minus H, which is fine, or something else, V minus Q plus F, things like that. But what? Why do we need Euler number? Uh, okay, it's not that clear to me. What I'm trying to say. Uh, so it is also doing the same thing that we discussed till now. We are just trying to get a boundary descriptor out there. But here you are just trying to compare two shapes directly instead of checking the boundaries for explicitly, right? So Euler number, as you see, C is the connected components and H is the holes. C is the connected components and H is the number of holes out there. No, sorry. Okay. So it can also be described by V, which is the number of vertices. If you have a nice shape out there, Q is the number of edges, and F is the number of faces out there. Okay. Yeah. So given this definition, we can very easily solve it. Not much to discuss. What is the number of vertices? How many number of vertices do we have? One, two, three, four, five, six, seven, eight, nine, 10, 11, 11. Okay, 10, 10. Yeah, 11. 11 vertices. And how many edges do you have? So number of vertices is 15 edges. Oh, yeah, two faces you can very clearly see 11, 13, 14, 15. So the number of edges are 50. So given this, we can uh, just put the formula out there. Edges is Q, faces is F, and vertices is V. So yeah, yes, 11 minus 15 plus 2, which is minus 2. So this is the Euler number for the specific star-shaped thing, which has two faces. There are holes. Any doubts with this question? Okay. They are holes, actually. They are not faces. Yeah, they are not filled, actually. They are empty. That's why they are given. Faces means when you have an object, so it should, I think someone is unmuted. They are not speaking. They can mute. Can everyone just mute themselves if they are not conversing at this point? Yeah. So what I was saying is yes. So this is filled actually. This part is filled. That's why it's a face. But these part is empty out there, which means it has not. It is not a face actually. So you don't consider this other part. Hope that clear. Yeah. Please mute yourself if you are not speaking. That will help conversing us. Someone is still muted. On. Okay. So just draw. Okay. Yeah. So we'll now do the run length encoding. So I just missed out a word, so I wrote it specifically here. Someone is still unmuted. Please mute themselves so that we can hear properly. Yeah. Okay. So yes. So we have this run length encoding that we need to do to compress this image. So for the given image, find the run length code. Given the white pixel is represented by 0, so the white is represented by 0 and the black is represented by 1. Okay. Given this specific thing, setup out there. Yes, there is one more thing that they mentioned that the digital system encodes the code used to represent the white. So this is the code that is used to represent the white pixel at the start of each row out there. Okay. Okay. So whatever your first element of the row will be, that will contain the specific zero out there. That's what I'd say. Okay. Given this, we'll start with the run length encoding. So how to start? Anyone out there? I'll just label it like this, or maybe I'll just copy that thing again. Okay, so we can just label things here like this. So in the class, there was a specific way in which run length codes were given, but the questions uh, the questions that we are solving, and I guess even you are given have been given a different way of computing the run length code. So we'll do that specific way of solving it. So how to do it is we'll first check how many white is there and then how many black is there per row and then just count it based on the number of occurrences. So how many whites are there at first per row? This is one white, then one black, then two whites, then the last one is one black. So your code will be like this for the first row, one, one, two, one. Second row, it will be one white, two blacks, then two whites. Third one will be two whites, two blacks, one white. Fourth one is three whites, one white and one black. Final one is one black, three whites and yeah, one black. Yes. Okay. So what we are doing is we are just seeing how many blacks and whites are there along a row. Along a row, we are just trying to compute how many blacks and whites are there. So if there's yes. So here along a row like this, if you go in this specific direction, then you see that there is one white, we wrote one. There is one black, we wrote one. Then there is two whites, we wrote two, and then there is one black, we wrote one. Okay. So we are trying to yes, one white, which is this one black, which is this one. There are two whites, which is this two black. Yeah, there are two whites then, and then this is one black. Last one is black. No, we are counting here. We are not really. Yes, yes, yes. We are just counting here along a row. Uh, yeah, we are just counting the number of occurrences. Counting the number of occurrences along a row. Yes, I'm not saying this is white or yes, one white, one black, two whites, one black. Yes. The next one is one, yes, two blacks, two white. Yes, yes, yes. Yeah, okay. So ultimately, what they wrote is that we also have to encode the white pixel at the start of each row. How is the white pixel represented? So here the white pixel in the memory is represented as a zero. So our final answer would be for first row we'll append zero out there because the first element represents the white pixel value. That's what we did, and then just copy other things out there. So for the second row, we are not going to repeat the same thing because this same the same thing will be repeated here again and again. So in the options as well, it's not given out there. So this is your final representation for the yes, your final representation for run length coding. Okay. Yeah, we have to add zero initially because they said that we have to represent which code white is out there, which code stands for the white pixel. That's what they mentioned here. Yes. So that's why we added zero out here. That's yeah, yeah. Because for other rows again, everything will be zero. So we are just adding the same information again and again. So we are just adding it for the first. Yes. Yes. Yeah, this is the answer. By the way. Yes, I agree that the last row is starting with black pixel. Yes. Yes, yes, yes. This is how the specific encoding scheme is. Yeah. Sorry. Okay. At least you can just follow the way it's given in the question. I mean, for the specific way in which the course is followed, you have to follow this way. You are right that we should mention here that first, it should not really be the first, just the white pixel value, but it should say which one is this. So probably all of these should get appended with zero initially, and the last one should get appended with one, because that will give us information whether the first one is a white or a black. And based on that, you can, yeah, this makes sense. I agree with that. But the options, I don't have such options. There are only four options out there, and you have to choose one of them. So, well, actually, if you implement it practically, you have to do it this way. But if you're attempting the exam, then you have to be careful of how to choose it. At least I don't have a specific answer of how to disambiguate which one is first white or first black with this given representation. If you add append zeros to or zero or one specifically out there, then it makes it very clear how to go ahead. Okay, so we will move on to the next one. This is again a similar question in the sense that we'll try to compress the image like the previous question, but we'll use a quad tree out there instead of the basic coding techniques that we used till now. So this is the question out there. So find the quad tree representation for the given figure. So find the quad tree representation for the given figure. If the division is in the order of northeast, southeast, southwest, and northwest, that means you have to first take the this specific quadrant northeast, then southeast, then southwest, and then northwest in the four cardinal directions from left to right. Sorry. So given the white pixel is represented by 1 and a black pixel is represented by 0 and gray pixel G is both 1 and 0. So that's what the convention also used in the lectures. So first you see the full image out there. What can you say? No, you have to check the full image first. I think a similar question we did, not for this specific application, but you first have to check the full image always. If the full image is same, then you can just write it W or B, white or black. But then here in the specific case, yeah, here in the specific case, we see that the full image is not white or black. So then we choose to the. Something wrong with one node. Okay, how should I do it? This is okay. Just give me a minute. Sorry. Mm, okay, it's not recording now. Okay, this fixed now, so we can continue. Yeah. So we have the specific case out there. First, as I said, that we'll have to we'll have to check the full image. Check full image. Since it is not homogeneous, what we have to do is we can now divide it into different parts. Full image is non-homogeneous. So given this, we now divide it into different parts, which is so as soon as you start dividing, what is the encoding that you do? You write a G. G means it contains both 1 and 0, the full thing. So I'll use that bracketing out there, which was given in the class, which makes things easier. So as soon as you write G, what can you do? Take, yeah, divide this out there, divide this out there like this. Yes, this is like dividing it into four quadrants. Once you divide it into four quadrants, what is it that you can do? Yeah, so the northeast part is this one. Yes, northeast is not this northeast, right? Isn't this northeast? Yeah, okay. So we'll check the northeast part. So northeast part is again gray, right? So we'll write a G here and then take a bracket again. As soon as you bracket it out, we can just write this divided again. So once again, given this thing, you check the northeast part again. This northeast part is not again. We have to take a G and then write and divide it. So we have done three levels of division, and you can also clearly see here with brackets as well as the divisions here. Okay, now you see here. So what is here? It is black. Yeah, and then yeah, you have to go like this: northeast, northeast, and then yeah, northeast, southeast, southwest, and northwest. So like this. You go like this. This is black, black, white, and white. Black, black, white, and white. Yeah. So once this part is done, we'll move on to the for bigger block. In the bigger block, we'll check for the same thing, which is the southeast part. Southeast again, you see that yeah. So you have to take another G since you divided it, and then you do this black, black, white, white. Now come to this part. Here it's homogeneous. So what it will be, we directly write the white part, and then here it's the black part. So once this whole thing is done, close the specific bracket out there. This is one, two, three, four blocks. So this bracket will close here. Okay. Given this, again, we move on to the next one. So we can do it now quickly. We divide it since you see that there are inhomogeneous regions out there. So again, so since we divided it, we take a bigger bracket. Once this bigger bracket is out there. We'll start from here. This is black, completely black, it is fine. This is not homogeneous, so you divide it again. This is black, black, white, 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 and then this is what? Black, homogeneous, this is white. Yeah, so the four parts are defined here. Then you come to this region. This region is fully homogeneous with white. So I'll directly write W. And for the fourth region, we'll have to divide because it's not homogeneous again. And again, if you see it here, we have to divide it all these three other parts as well. So in this region again, we see the northeast part. The northeast part is white. So we tend to write white here. So we'll write white here for this northeast part. Oh, sorry, it's black. Sorry, this is black. What about this? We divided it, so we'll write a G, and then inside G it will be white, white, black, black. Yeah, white, white, black, black. What about this one? This will be again we have to divide. We divided it, so we'll write Z. It will be three W's and then a single B. And the last one is since we divided it, so we are writing G and then it's WW. Sorry, yeah, WW B W. WWBW. So this is your final answer. Final answer is just removing the brackets and then writing it in a straightforward manner. So I wrote this part, now I'm rewriting this part. And similarly the other ones as well. So is this question clear? This is the final answer. Okay, so if this question is clear, we can move on to the next one. So this is the quad tree representation. So why is it quad tree, by the way? Because we are always dividing it into four parts. So each node is divided it into four parts. So it's not a binary tree, it's a quad tree. So if you divide it into eight parts, it is an octree, and similarly the conventions follow. Okay, so given this, uh, well, for 2D case, you can divide into a quad tree. If you are 3D data, then you divide it into octree. Yeah, yeah. For 1D, only binary can happen. For 2D, quad tree. For 4D, sorry, 3D, it's octree. For 4D, it's I forgot some fancy. So it's 2 to the power something as you 2 to the power d, where d is the dimension. That's how you do it. Okay. So where are we? We are here. The representation that supports matching even in the absence of scale and orientation information is what. So these are the representation of what at first place. These are shape descriptors. All four of them are shape descriptors. The point is now which one is useful where it depends. So we'll first go with polygon approximation. What does it do? Polygon approximation. Anyone? So that's what we did sometime back, right? We not really did sometime back, sorry. But so if you have some weird shape like this, you can approximate it by a polygon, for instance. This is what pentagon, for instance. You can just fit a pentagon to this specific shape, and then you can say that it uh, is a polygon approximation of the object. So this is the approximation, and this is the actual shape. Okay. So given this, what do you think? How do you construct polygon approximation? Well, I might not be exactly right in terms of drawings, but you first take two extreme points actually. So this is not the right approximation of the polygon. You have a better approximation if you choose this and this as the endpoints. Once you have these two endpoints out there, you have to take perpendicular bisectors in such a way that they reach out to the maximum. These bisector lengths are maximum. If these lengths are maximum, then you choose all these points out there for fitting a rectangle out here. It's the best way to do. Take the maximum extreme endpoints, take perpendicular bisectors, then see where it intersects to the object, and then fit a rectangle out there. This would be the polygon approximation. This is some other approximation. It's also polygon, but not the best one. This is polygon approx with rectangle. The question asks, you don't have scale and orientation information. That means it's absent. Can you still do polygon approximation? Yes or no? Why do you say so? So yeah, you're given the object like this in that black curve out there. So given the object, you don't need anything else. You can just get polygon approximation independently of how the object is rotated. If the object is rotated, your polygon approximation will automatically get rotated. You don't have to worry about the orientation, how it is out there. So if you rotate like this, your everything approximation, all approximations will also get rotated like this. If you increase the size, for instance, if your size increases like this, even then your final size of the approximation also increases. So you don't have to worry about those things. So even in the absence of scale and orientation information, you don't explicitly need to know how much is the scale and orientation of the object. Whatever you give, the algorithm will work out. So this supports scale and orientation information. How about chain code? What do you do in chain code? Yeah, so if you have four or eight directions, you label the directions, right? And then based on those labels, for instance, if I choose the same object out here, so this one, okay, I should use a better refined directions than this. These ones, 0, 1, 2, 3, 7. Okay. So if I have these directions, now you approximate it with this specific direction, which is one out there. Again, this is one out there. This is one, probably one. This is seven. So you're trying to approximate it based on the directions. Whatever ultimately the code gets generated, this code is dependent on the orientation, right? So now if I rotate the object like this, the one might get two if you rotate it by this 45 degrees angle. So all ones will become two, all sevens will become zero, So it is dependent on the orientation. So, well, they are talking about chain code here and not the shape number. Shape number will be same. That's why. Yeah, yeah. It's that's why they made it in a way that they take circular code. I mean, it's circularly same. And to make it unique, they take the minimum magnitude. So the Fourier descriptor. What do you think about Fourier descriptor? Hmm? What do you do in Fourier descriptor? As I said, just take all the XY locations out there, which turns out to be S of K, which is a complex signal consisting of X plus J times Y, and then take the Fourier transform. Fourier transform, specifically DFT. So if you remember, the Fourier transform shifts based on how this input Fourier series is out there. If you rotate the signal, your output will change. If you translate, your output will change. Just check the properties slide out there that was given in the lecture. So there is a property for rotation, a property for translation, scaling, and the starting point as well. So as soon as you change these or rather transform this input signal with those transformations, the output Fourier transform will also be appropriately changed. So they are asking for scale and orientation. Yes, the Fourier descriptor is affected by that. What about statistical moment? Statistical moment. How do you check statistical moments? This is mu1 is summation over k probably xk minus mu0 into PDF at xk. That's how it is defined. So mu n is xk minus mu0 to the power n. So this is the nth order moment. So here it depends. You can clearly see that it depends on the scale, right? If the scale is small, then mu naught will be small. Everything will be small. If the scale is big, your mu naught could be big, and everything could be big. So simple example is like if the points are spread in a small area, your variance will be small. But if your points are spread in a larger area, the variance is high, right? Variance is what the second order moment. Yes. If the variance is high, because the scale of the same points is more, that means it is dependent on scale. Again, now if you see for the rotation part, this for yeah, with the rotations, these specific values will change, xk and mu k. So ultimately, mu1 will also change. So with all of this, we conclude that even statistical moment does not support matching in the absence of scale and orientation. So you need to have some information of scale and orientation of the object when you compute features using other three descriptors like statistical moments, Fourier descriptor, or chain coding. So if you don't have the other information out there, even if you extract features from the objects, you cannot match two different objects and say whether they are same or not. Okay, is this question fine? Any doubt? Should be zero, right? Ah, sorry, zero is fine. This one should be one. Mean is one. Sorry, you're right. So yeah, you can take zero. Zero means it's just should be one. The PDF should sum to one. Probability mass function rather, since it's a discrete case. The PDF should sum to one. So the mu zero should always be one. Mu one is your mean and mu two is variance. Yes, you're right. Sorry. Thanks a lot. Thanks for the correction. Okay. Okay. What is this giving us? Another theoretical question. Which of the following statements is false about signature in object representation? What is signature in object representation? So if you have an object like this, just take the center of the object, keep a reference axis, which is the x-axis generally, and check the theta. And at a particular theta, check how far it is. So what we are ultimately doing is checking the radius versus theta for a given object. If it's circular, then it's a flat line. If it's square like this, we discussed that it will be like this, repeating again and again. So this will be at pi by 4, this will be at pi by 2, things like that. Okay. So which of the following statements is false? Okay, we'll see. This is a 1D representation of a boundary. So is it a 1D representation? Yes, no. R is only a function of theta, right? Theta is a single variable. So is it a 1D representation? Yes. So instead of explicitly typing, rather storing all the pixel values x comma y of these boundaries, you can just store this get the function out there of r with respect to theta. So it's a 1D variable. Yeah. The distance from center point to the border represented as a function of angle. Yes. So r is represented as a function of theta. So it is true, independent of translation, rotation, and scaling. Translation independence, is it independent of translation? Yes or no? Why no? So if you translate the whole object, the center of the object won't change, right? We compute the distance from the center point. Yes. I mean, the center point changes. The point is the distance between the center point and the boundary does not change. Yes. The relative displacement is same for both. So the distance won't change. So once the distance won't change, it won't be affected by translation. So translation is independent of translation. True. Sorry. Did you say something? Okay. No, no. We'll first finish it off. Rotation. What about rotation? If you rotate this object, this is fine. But if you rotate the square, the function changes, right? Yeah. So this is the false one. What about scaling? If you increase the size, the graph also changes. The graph scale increases. Yes. Agrees? Agreed. So if you increase the size, the distance from the center of the object to the boundary increases. Yes. So this whole thing will just get stretched out. The graphs will be stretched out. So this is not independent of all three. So this is the right answer. Okay, is this fine? Okay, then we'll just do the last question for today. And then we can leave. Yeah. So which of the following statements is false about B-spline curve? Okay. So what are B-splines? We just discussed briefly. What is B-spline? The first option is defining B-spline. Well, you have to choose the false ones, but anyways. What is B-spline? It's a curve of order n, which is a piecewise polynomial function of degree n minus 1. Is this right or wrong? Yeah, it's true. So if you just take, for instance, constant functions and then add them up, these are two different constant functions, and then add them up, what you get is a function like this. So here, when you add them up, this plus this, okay, it might look weird to be like this. Okay, I'm not getting a specific example out here, but yes, the point is if you add polynomial functions of the degree n minus 1, you get order n polynomial functions, which is a B-spline curve. I think there are examples given in the lectures. You can refer to that. It is necessary for blending function to become non-zero. No, you can have constant function over some area, right? This is one of the examples in the lecture. So you just have this as non-zero part, this other parts as zeros. So this is false. What about the third option? B-spline curve provides a local control through the control points over each segment of the curve. Yes, as we see that if we increase the number of control points, even with lower order B-spline curves, we can fit a good object out there, object boundary. So this is true. What about the fourth one? The degree of B-spline curve polynomial does not depend on the number of control points. Yes, both are independent parameters. You can choose as per your requirement. So it does not depend on the number of control points. Okay, is this question clear? Yeah. Okay then. I guess then we can stop the session today here. Thanks for joining. We'll come back same time next week to discuss the next week's lectures. Okay. LBP. Okay. What is that about? Depends on convention. What convention was used in the class? So I guess I did a question on LBP. I just don't remember the convention. So probably it's 2 to the power 0 that you start. Probably. Okay. So, oh, okay. There is an ambiguity then. Maybe you can just post it on the forum there, right? Just post it on the forum. What is the convention that should be used for the exam? Yeah, that will be better because I don't know what they'll follow for setting up the question paper. It's there. Yeah, there was a problem, technical glitch out there from the NPTEL side. You can always check for the, yeah, YouTube videos are always there. I mean, on my channel, you can just check for the course code NOC23-EE39 and you can check all the videos. And now, I mean, that problem, the technical glitch has also been solved. So you can access these documents as well. You can just check for problem solving sessions, which is on the left bar of the NPTEL uh, course page. Yeah, where you see other lectures, right? Yeah, you can just check it. Yeah, yeah. No, it was fixed yesterday, I guess. So maybe you should see it today. It should be fine. Yeah. Okay then. Thank you guys for joining. We'll see you next week. Bye bye. Yes, someone raised a hand. Yeah. Yes. I guess it will be done next week, right? Okay. Okay. Mm-hmm. 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 Okay. Binary image. Yeah. Mm-hmm. Okay. Okay. So before binarization, do you see whether just after thresholding, do you see whether the specific part where the knee is present is coming in that or not? So after, I mean, as soon as you threshold the image, right? Can you see the knee? No. So the threshold used is probably not the correct one. So you can just use Otsu thresholding, for instance. There are many other thresholds out there. Mhm. Okay. Okay. So with this specific formula, you are able to see the knee part at least properly. It's hiding. What you're trying to say is what? Yes, what you're trying to do is you will first extract the knee part using this binarization, and then you want to do